The second planet from the Sun was supposed to be the straightforward one. Not simple, exactly, but knowable. When the first generation of planetary scientists began mapping the solar system in earnest, Venus presented itself as a world that fit neatly into existing categories. Similar in size to Earth, similar in mass, positioned at a distance from the Sun that, on paper, did not look obviously hostile. Observers called it Earth's twin. Some called it Earth's sister. For a brief window in the middle of the 20th century, there were serious scientific proposals that Venus might harbor tropical forest beneath its permanent cloud cover, a warmer, wetter version of a world we already understood. That picture collapsed quickly. The first spacecraft to survive entry into the Venusian atmosphere confirmed what spectroscopic data had been suggesting for years. The surface temperature averages around 460 degrees Celsius. The atmospheric pressure at ground level is roughly 90 times that of Earth, at sea level equivalent to the pressure found nearly a kilometer beneath the surface of our oceans. The clouds that once suggested mystery are composed primarily of sulfuric acid droplets. The planet rotates so slowly that a single Venusian day is longer than a Venusian year, and it rotates in the opposite direction from most of the solar system, so that the sun rises in the west and sets in the east for any observer unfortunate enough to be standing on the surface. Venus, it turned out, was not easy. It was among the most hostile environments in the known solar system. And yet, the assumption of knowability persisted. Scientists adjusted their models, updated their frameworks, and moved on. The surface was hostile, that was settled. The chemistry was understood well enough. The cloud layers had been studied by multiple Soviet Venera probes, by Pioneer Venus, by Magellan, by Venus Express. The planet had been mapped, measured, and categorized. Whatever mysteries remained were considered manageable. Venus was a closed chapter in one sense, even if not every question had been answered. That assumption held for decades. Then, in September of 2020, a team led by astronomer Jane Greaves announced that they had detected phosphine in the atmosphere of Venus using the James Clerk Maxwell telescope in Hawaii. A follow-up analysis using data from the ALMA Observatory in Chile appeared to support the finding. The detection was, on its face, extraordinary. Phosphine, molecule composed of one phosphorus atom bonded to 3 hydrogen atoms, is not easily produced by the kinds of geological or photochemical processes known to operate on Venus. On Earth, it is associated almost exclusively with 2 sources: industrial manufacturing and biological activity. Anaerobic microorganisms produce it as a metabolic byproduct. It appears in swamps, in the intestines of animals, in environments where life operates without oxygen. The implication, stated carefully by Greaves and her colleagues, was that something in the Venusian cloud layer might be producing phosphine through a process that existing abiotic chemistry could not adequately explain. They were not claiming to have found life. They were claiming to have found a molecule whose presence demanded an explanation, and that the most straightforward explanations were not sufficient. The scientific community responded with immediate and intense scrutiny. What followed over the next 2 years was not a confirmation. It was not a clean refutation either. It was something considerably more uncomfortable, a prolonged, technical, and still partially unresolved argument about instrument calibration, data processing pipelines, spectral line identification, and the difficulty of making precise chemical measurements across 41 million kilometers of space. The detection shrank under reanalysis. The confidence interval collapsed. The abundance initially reported was revised downward significantly after errors were identified in the ALMA data processing. Some researchers concluded that the signal was too weak to be distinguished reliably from noise. Others maintained that a residual signal, smaller than first reported, but potentially real, remained in the data. The phosphine question is not fully closed. But the story of how it opened and what happened when the scientific community tried to answer it reveals something that rarely receives the attention it deserves. It reveals how much of our confidence in biosignature science rests on assumptions we have not fully tested. Venus was the planet we thought we understood. It was the neighbor, the twin, the world close enough to study with ground-based telescopes and near enough to visit with robotic spacecraft. If we cannot reliably characterize the chemistry of the atmosphere of Venus from Earth, that raises a question that extends well beyond one detection controversy on one planet. It raises a question about every other world we have studied from a distance, every exoplanet atmosphere parsed by spectroscopy, every distant moon assessed by remote observation, every candidate biosignature identified in the data across hundreds or thousands of light years. The Phosphine episode did not simply reveal a mistake. It revealed the edge of what our current instruments and methods can actually do, and the edge turned out to be closer than most people expected. To understand why the phosphine detection produced the response it did, it helps to understand the state of biosignature science in the years leading up to September 2020. The search for life beyond Earth had been, for most of its history, a discipline defined by patience and indirect evidence. SETI listened for radio signals and found nothing definitive. Mars missions searched for organic chemistry in the soil and produced results that remain contested decades later. The distance of exoplanets changed the scale of the conversation dramatically. Suddenly there were thousands of worlds to consider, rather than a handful, but it also sharpened an underlying problem. Detecting a planet is one thing. Determining whether that planet hosts life is something else entirely, and the gap between those two achievements is vast. Biosignature science emerged as the proposed bridge. The core idea is straightforward in principle. Certain molecules, when present in a planetary atmosphere in quantities that cannot be explained by known geological or photochemical processes, might indicate biological activity. Oxygen is the classic example. Earth's atmospheric oxygen is almost entirely the product of photosynthesis, and without continuous biological production, it would react away within geological timescales. Methane is another candidate, since it is destroyed quickly by ultraviolet radiation and must be continuously replenished to remain detectable. Nitrous oxide, dimethyl sulfide, and several other compounds have been proposed as potential biosignatures under specific conditions. Phosphine became a serious candidate for a specific reason. A 2019 paper by Clara Souza Silva and colleagues examined its detectability in exoplanet atmospheres and concluded that, on rocky worlds without large-scale industrial activity, the presence of phosphine in meaningful concentrations would be very difficult to explain without invoking biology. The logic was compelling. Phosphine requires energy to form. It is thermodynamically unstable in oxidizing environments. The production pathways available through lightning, volcanism, or photochemistry were calculated amounts, orders of magnitude, below what telescopes would be capable of detecting. If you saw phosphine on a rocky planet, you needed a source. And the most efficient known source, by a considerable margin, was life. This background gave the Greaves announcement its particular weight. The team was not interpreting an ambiguous signal through a speculative framework. They were applying a methodology that had been developed and published in advance by a separate group precisely for this purpose. The detection appeared to slot directly into an established scientific program. The molecule was the right molecule. The planet, despite its surface conditions, had a cloud layer where temperatures and pressures fell within ranges that some researchers had proposed cautiously as potentially habitable for microbial life, cool enough, pressurized enough, with available chemical energy. The initial reported abundance was around 20 parts per billion. That figure, even at the time, was noted as surprisingly high. models of Venusian atmospheric chemistry suggested that phosphine should be destroyed rapidly by the sulfuric acid environment. To maintain a detectable abundance, whatever was producing it would need to do so continuously and at a substantial rate. Some researchers calculated that this implied a biological productivity roughly comparable to that found in certain regions of Earth's oceans. That was not impossible, but it was a striking number for a planet that had spent the previous 50 years being described as definitively lifeless. The data came from 2 independent observatories, which strengthened the initial impression of reliability. The James Clerk Maxwell Telescope provided the original detection. The ALMA array, one of the most powerful radio telescope facilities on Earth, appeared to confirm it. 2 instruments, 2 datasets, 1 consistent signal. The methodology appeared sound. The calibration was assumed to have been handled correctly. Publication in Nature Astronomy, one of the highest profile journals in the field, added another layer of apparent validation. What the initial announcement did not fully communicate was how close to the detection limit the signal actually sat. Phosphine produces a spectral absorption feature, a specific frequency at which it absorbs radiation, leaving a recognizable dip in the spectrum of light passing through a planetary atmosphere. Identifying that feature requires distinguishing it from the background noise of the instrument, from other molecular signatures that occur at nearby frequencies, and from artifacts introduced by the data processing pipeline itself. The margin between a real signal and a convincing noise feature is not always large, and the protocols for establishing that margin reliably are more contested within the field than most outside observers would assume. Within weeks of publication, other research teams began working through the data. An independent reanalysis of the ALMA data identified a calibration error in the data processing pipeline. When the error was corrected, the reported abundance dropped significantly from around 20 parts per billion to something closer to 1 part per billion, with substantial uncertainty on either side of that estimate. A separate group examining the James Clerk Maxwell Telescope data raised questions about whether the spectral feature being attributed to phosphine might instead be partially or wholly explained by sulfur dioxide, a molecule known to be present in the Venusian atmosphere, and one that produces a spectral feature in a nearby, potentially overlapping frequency range. The detection did not disappear, but it became much harder to read. 1 part per of phosphine, if real, is still unexplained by current models of Venusian chemistry. The abiotic production pathways remain insufficient at that concentration too, though the gap between what known processes can produce and what the data might show is considerably narrower than the original announcement suggested. The possibility that the signal is instrumental noise, spectral contamination, or a combination of both cannot be ruled out with the data currently available. And Venus, unlike Mars or the moons of the outer solar system, has not been visited by a spacecraft capable of in situ atmospheric sampling in more than 3 decades. The detection that briefly appeared to be the most significant finding in the history of astrobiology rested, in the end, on a signal that could not be cleanly separated from the limitations of the instruments that produced it. That is not a scandal. It is not a failure of individual scientists. It is a description of where the boundary of observational capability actually sits. And that boundary matters enormously for what comes next. The reanalysis of the ALMA data revealed something that extended well beyond the phosphine question. It revealed how a measurement can pass through multiple layers of scientific review and still carry a fundamental error inside it. The calibration problem was not obvious. It was not the kind of mistake that announces itself during a standard quality check. It was embedded in the data processing pipeline, the software and procedural framework used to convert raw telescope output into interpretable spectral data. Identifying it required independent researchers working through the same pipeline with a different set of eyes, applying different assumptions, checking steps that had been assumed correct. This happens in science. Errors surface through replication attempts, through independent analysis, through the sustained pressure of a community examining a high-profile claim. The system, in that sense, worked. The error was found, the abundance was revised, the confidence interval was widened to reflect genuine uncertainty rather than the narrow range that had initially been reported. But the timeline matters. The original paper appeared in September 2020. The calibration error was identified in the months that followed. During that interval, the detection was widely reported as one of the most significant findings in planetary science in years. The gap between what the data could actually support and what the announcement implied was filled, briefly but consequentially, by scientific momentum and public attention. This is not unique to the Phosphine case. It reflects a structural feature of how major scientific announcements propagate, and it has particular relevance for biosignature science, where the stakes of a false positive are unlike those in almost any other field. Consider what a confirmed detection of life beyond Earth would mean. It would not merely be a scientific discovery. It would be a civilizational event. It would reframe the question of what life is, how common it might be, what our place in the universe actually represents. The pressure to be first, to be certain, to announce, rather than to wait, that pressure does not disappear, simply because scientists are aware of it. It operates on institutions and individuals in ways that are subtle and sometimes invisible even to those experiencing it. Phosphine on Venus was never claimed as confirmed life. Greaves and her colleagues were careful, in the original paper, to frame the detection as an anomaly requiring explanation, rather than as proof of biology. But the gap between what scientists write in a paper and what the broader conversation hears is rarely narrow, and the phrase, unexplained by known abiotic chemistry, carries an implication that travels faster than the caveats surrounding it. What the Phosphine episode made visible, then, was not primarily a story about one detection on one planet. It was a demonstration of how the biosignature pipeline functions under pressure from initial observation, to data processing, to peer review, to publication, to public communication, and where the weakest points in that pipeline actually sit. The weakest point is not where most people would expect to find it. It is not in the willingness of scientists to make things up. It is not in the peer review process, failing to catch obvious errors. It is in the space between what an instrument can measure and what a researcher needs it to have measured. Telescopes do not produce unambiguous readings. They produce data streams that require processing, calibration, modeling, and interpretation at every stage. Each of those stages introduces choices. Some choices are well constrained. Others involve judgment calls that reasonable scientists might make differently. And when the signal being searched for is faint, when it sits close to the detection limit, when it overlaps in frequency space with other molecular signatures, the accumulated weight of those choices can produce a result that looks cleaner than the underlying data actually supports. This is the epistemological core of the Venus problem. Not that the detection was wrong, though it may have been, but that the process of determining whether it was wrong required months of independent work by multiple research teams, revealed an error in a major observatory's data pipeline, and still arrived at a result that remains genuinely uncertain. 1 part per billion of phosphine, if present, is unexplained. Whether it is present is still not fully resolved. Now extend that problem outward. The nearest exoplanet, likely to have a rocky surface, sits more than 4 light-years away. The exoplanets currently considered most promising for atmospheric characterization, those orbiting in the habitable zones of nearby stars, small enough to be rocky. Positioned so that they transit their host star from our perspective, are dozens to hundreds of light-years distant. The atmospheric signals from those worlds arrive attenuated across that entire distance, filtered through the glare of their host stars, compressed into spectral features that are often smaller than the noise floor of even the most sensitive instruments currently available. The James Webb Space Telescope represents a genuine leap in atmospheric characterization capability. It has already produced atmospheric detections for several exoplanets, including carbon dioxide identification that were not possible with previous facilities. Researchers are actively working through its data, looking for the molecular signatures that biosignature frameworks predict. The science is moving forward, but the Phosphine episode established a reference point that should inform how that progress is interpreted. If a signal at 1 part per billion or even 20 parts per billion in the atmosphere of the planet 41 million kilometers away, the neighbor, the twin, the world reachable by spacecraft within months, can generate this level of ambiguity and this much downstream interpretive work, then what should be expected from a signal detected at interstellar distances in an atmosphere that has never been sampled directly, processed through an instrument operating at the edge of its sensitivity range? The answer is not that biosignature science is futile. The answer is that the confidence required to say, "We have found something," should be calibrated to a much higher standard than the Phosphine episode initially demonstrated. What Venus exposed is the gap between detecting a signal and understanding what produced it. That gap, it turns out, does not shrink simply because the instruments improve. In some respects, as sensitivity increases, and since signals closer to the noise floor become accessible, the gap widens, more detections become possible. More of them will sit in ambiguous territory. More of them will require the kind of sustained, difficult, multi-year reanalysis that the Phosphine question demanded. The planet closest to us offered a preview of that problem. It was not a comforting preview. There is a version of this story that ends with instrumentation. Build better telescopes. Develop more sensitive detectors. Refine the data processing pipelines. Send spacecraft directly to Venus to sample the cloud layer in situ, rather than inferring its composition from 41 million kilometers away. The Phosphine problem, in this telling, is a technical problem, real but solvable. A temporary limitation of current capability, rather than a fundamental constraint on what biosignature science can achieve. That version is not wrong. Better instruments would help. In situ sampling would resolve questions that remote spectroscopy cannot. Several proposed Venus missions, including NASA's Da Vinci concept and ESA's Envision orbiter, are designed to address exactly this kind of gap. Da Vinci in particular was selected for development specifically to probe the Venusian atmosphere with a descent probe capable of direct chemical measurement. If it flies and performs as designed, it will either detect phosphine at a level consistent with the residual signal or establish an upper limit that closes the question more decisively than any ground-based reanalysis could. That would be progress, real, meaningful progress. But the instrumentation story by itself leaves something unexamined, because the problem that Venus revealed is not only about the sensitivity of telescopes or the accuracy of data pipelines. It is also about the interpretive frameworks. Scientists bring to a detection the theoretical models that determine what a given molecular abundance means, where it comes from, and whether it requires biology to explain. Phosphine was flagged as a potential biosignature because the known abiotic production pathways on Venus appeared insufficient to count for even modest concentrations. That assessment rested on models of Venusian atmospheric chemistry, models that are themselves built from incomplete data, from laboratory measurements of reaction rates, conducted under approximate, rather than exact Venusian conditions, from assumptions about cloud layer composition and vertical mixing that have not been validated by direct sampling in over 3 decades. When the detection appeared, several research teams began revisiting those models. What they found complicated the picture in ways that had nothing to do with the signal strength. One group examined the potential contribution of volcanic activity more carefully than previous models had. Venus is almost certainly volcanically active surface features imaged by Magellan and, more recently, reanalyzed using archival radar data suggest ongoing or geologically recent volcanism. The rate and character of that volcanism is poorly constrained. If Venus experiences episodic volcanic outgassing events, the chemistry of the cloud layer at any given time might look significantly different from what steady-state models predict. Phosphine production through volcanic pathways remains below what the original detection implied, but the uncertainty on those production rates is larger than it was initially assumed to be. A separate line of investigation examined the sulfuric acid chemistry of the cloud layer itself. The Venusian clouds are not uniform. They exist in distinct layers at different altitudes, with different temperatures, pressures, and chemical compositions. The reactions between sulfur compounds in those layers are complex and not fully characterized. Some researchers proposed that unusual sulfur chemistry, operating under conditions not well represented in existing laboratory datasets, might produce phosphine or phosphine-like spectral features through pathways that had not been previously considered. These proposals remain speculative. None have been confirmed experimentally, but their existence illustrates a broader point. The models used to define what counts as unexplained are themselves products of incomplete knowledge. This creates a circularity problem at the heart of biosignature science. A biosignature is defined as a molecule or feature whose presence cannot be adequately explained by known abiotic processes. But known abiotic processes are not a fixed, fully characterized set. They are a catalog that expands as planetary science advances, as laboratory measurements improve, as new reaction pathways are identified. A molecule that appears to require biology today may turn out to have perfectly adequate geological explanation once the relevant chemistry is better understood. Oxygen is sometimes cited as an exception, a molecule so overwhelmingly dominated by biological production on Earth that it seems safe to treat as a reliable biosignature. But even oxygen has been shown to be producible through abiotic photolysis of water vapor under specific conditions, and researchers studying airless bodies in our own solar system have detected trace oxygen atmospheres that have nothing to do with life. The history of biosignature science is partly a history of candidates being proposed and then eroded. Methane on Mars appeared intermittently in orbital and ground-based measurements for years, generating significant discussion about possible biological sources. The signal has proven difficult to reproduce consistently, and the most recent data from the Curiosity rover's tunable laser spectrometer has produced readings that conflict with what the Mars Express orbiter detected from above. The two data sets cannot currently be reconciled. The methane question on Mars is not closed, but it has not produced a confirmed detection either. Venus was supposed to offer a cleaner case. The phosphine methodology had been worked out in advance. The molecule was well chosen. The detection appeared solid, and yet the result sits in the same uncomfortable territory, real enough to take seriously, uncertain enough to prevent any firm conclusion, dependent on models that are themselves open to revision. What this pattern suggests is not that life does not exist elsewhere. It suggests something more methodologically troubling. It suggests that the tools currently available for detecting biosignatures, both the instruments that gather the data and the theoretical frameworks that interpret it, may not be capable of producing the kind of unambiguous result that the question demands. Detection without certainty is not the same as no detection, but in a field where the most important thing is distinguishing biology from chemistry. The difference between a signal and noise, between an unexplained abundance and an inadequately modeled one, is everything. Venus forced that distinction into the open. The planet was close enough to study carefully, interesting enough to attract serious attention, and chemically complex enough that the careful study produced not an answer, but a clearer map of the problem. That is genuinely useful. Science proceeds through exactly this kind of refinement. But useful is a different word from reassuring. And the map that Venus produced shows a terrain considerably more difficult to navigate than the field had generally assumed. If the nearest planet cannot be read cleanly, the more distant ones are going to require something more than better telescopes. They are going to require a level of interpretive confidence that the current state of Biosignature science has not yet demonstrated it can reliably achieve. There is a question that sits underneath the Phosphine controversy that rarely gets asked directly. Not whether phosphine is present on Venus. Not whether the instruments were calibrated correctly. Not whether the abiotic chemistry models need updating. Those are the technical questions, and they are important. But beneath them is something older and harder to resolve. What would it actually take to convince us? Not convince in the casual sense, not the level of evidence required to generate a press release or produce a trending headline. The deeper question: what standard of proof would be sufficient to support the claim that life exists somewhere beyond Earth? Given everything the Venus episode revealed about how biosignature detections behave under scrutiny, this question has been discussed within astrobiology for years, but the phosphine case gave it a specificity it previously lacked. Before September 2020, the conversation about confirmation standards was largely hypothetical. Researchers could debate in the abstract what a genuine detection would need to look like. After the phosphine announcement and its subsequent reanalysis, the debate acquired a concrete reference point, a real detection, real ambiguity, real disagreement, real revision, and a real demonstration of how quickly an apparent discovery can become an open question. The emerging consensus within the field, if it can be called that, is that no single biosignature detection will be sufficient. The bar, post-Venus, has effectively shifted toward what researchers call a biosignature ensemble, a combination of multiple independent lines of evidence, each of which individually might be explicable by abiotic chemistry, but which together create a pattern that becomes progressively harder to account for without biology. Oxygen combined with methane in a specific ratio. Nitrous oxide at concentrations above what photochemistry can sustain. Phosphine alongside other molecules that biological activity is known to co-produce. No single molecule, no single measurement, a pattern that converges. This is a more defensible standard than what the Phosphine case applied. It is also a considerably more demanding one. Meeting it requires not just detecting a molecule, but characterizing enough of a planetary atmosphere to identify co-occurring signatures, distinguishing them from each other and from noise, confirming their abundances across multiple observations and multiple instruments, and doing all of this for worlds that in most cases cannot be visited directly within any foreseeable time frame. The James Webb Space Telescope can, in principle, characterize the atmospheres of certain nearby rocky exoplanets, those orbiting in the habitable zones of dim red dwarf stars, positioned favorably for transit spectroscopy. Early results have been instructive, but also sobering. The TRAPPIST-1 system, which contains several Earth-sized planets at potentially habitable distances, has been observed repeatedly. Some of those planets appear to lack thick atmospheres entirely. The data, for others, remains ambiguous, characterizing an atmosphere well enough to search for a biosignature ensemble, rather than simply detecting or ruling out an atmosphere's existence, requires an amount of observing time that strains even the generous allocation available to high-priority targets. The next generation of ground-based extremely large telescopes may improve this situation meaningfully. The extremely large telescope under construction in Chile, the 30-meter telescope, and the giant Magellan telescope are designed in part with atmospheric characterization in mind. Combined with space-based facilities, they represent a genuine step forward in sensitivity. Whether that step is large enough to reliably identify biosignature ensembles in exoplanet atmospheres within the next 2 or 3 decades is a question the field has not answered with much confidence. Meanwhile, Venus remains the most instructive case available. Because Venus is not only a story about a failed detection, it is a story about a planet that, by the standards of biosignature science, should have been the easiest possible test, close enough for detailed spectroscopy, close enough for spacecraft visits, studied continuously for more than 60 years, and still, the question of whether its atmosphere contains an unexplained molecular abundance, not life. Just an unexplained molecule cannot be conclusively answered with the evidence currently available. Some researchers have pushed back against this reading of the episode. They argue that the Phosphine case demonstrates the system working correctly, that science is supposed to involve challenge, reanalysis, and revision, and that the eventual convergence on uncertain but more honest result is exactly what the process should produce. There is something to that argument. The reanalysis did happen. The error was found. The field updated its estimates. No one defended the original abundance in the face of contradicting evidence. But this reading misses something about the specific demands of biosignature science. In most fields, an initial detection that is subsequently revised downward is a normal part of the process. The revision refines the result, and eventually, a cleaner measurement settles the question. In biosignature science, the claim being evaluated is not simply a measurement. It is a causal attribution and argument that the quantity being detected cannot be explained without invoking a particular class of process. That causal attribution is far more sensitive to uncertainty than a simple measurement would be. Revising an abundance estimate from 20 parts per billion to 1 part per billion does not just change the number. It changes the entire explanatory challenge. It narrows the gap between what abiotic models predict and what the data shows, and in doing so, it shifts the detection from clearly anomalous to potentially within the noise of an inadequately modeled system. That shift matters in a way that has no close parallel in other fields. It is the difference between something that demands explanation and something that might just be measurement uncertainty dressed in suggestive clothing. Venus, in this sense, did not merely test the instruments. It tested the interpretive framework. And the interpretive framework, it turned out, was more fragile than the instruments, more dependent on assumptions, more sensitive to model revisions, more vulnerable to the kind of uncertainty that accumulates when a planet's chemistry is known primarily through remote observation rather than direct sampling. The hardest part of this is what it implies going forward. If Venus' neighbor, twin 60 years of study, sits at the edge of what biosignature science can reliably interpret, then every world beyond it sits further past that edge. Every exoplanet atmosphere parsed by transit spectroscopy is further away, less characterized, more dependent on models built from incomplete data, more susceptible to the same gap and understanding gap that the Phosphine episode exposed. The question of whether we can recognize life if we find it is not a question about instruments alone. It is a question about whether our frameworks for interpretation are adequate to the task. And Venus, the planet that was supposed to be easy, offered the clearest available evidence that they may not yet be. Step back far enough, and the Venus episode resolves into a single uncomfortable shape. We built instruments capable of detecting molecules across tens of millions of kilometers of space. We developed theoretical frameworks for identifying chemistry that life alone might produce. We identified a candidate world, not distant, not hypothetical, but the planet directly adjacent to our own, the one that shares our sun at nearly the same distance, the one that has been continuously studied since before the first humans walked on the moon. We pointed our best telescopes at its atmosphere and asked the simplest possible version of the question. And the atmosphere answered in a language we could not quite read. That is not a metaphor. It is a precise description of what happened. The signal was there, or it appeared to be. The molecule was the right molecule. The methodology had been constructed in advance specifically to handle this kind of claim. And still, 2 years of intensive reanalysis by multiple independent research teams could not produce a definitive answer. Not because the scientists involved were careless, not because the field lacked rigor, but because the measurement sat at the edge of what the instruments could resolve, and the interpretive models sat at the edge of what planetary science currently understands about Venusian chemistry. And when two edges meet, the result is not clarity. It is a question shaped like an answer. This is the position biosignature science now occupies. Not paralyzed, the field continues to develop. Instruments continue to improve. The theoretical frameworks continue to be refined by exactly the kind of pressure the Phosphine case applied. But the position is more exposed than it appeared before September 2020. The assumption that a sufficiently sensitive instrument pointed at the right molecule in the right atmosphere would produce a readable result has been tested against the nearest available candidate. The result was not a confirmation and not a refutation. It was a demonstration of how much interpretive work lies between a spectral feature and a conclusion. Consider what this means for the broader search. The TRAPPIST-1 system sits roughly 40 light-years away. The planets orbiting within its habitable zone are among the most studied exoplanet candidates, currently accessible to atmospheric characterization. 40 light-years is, by cosmic standards, almost nothing, a negligible fraction of that distance to the galactic center, a rounding error against the diameter of the observable universe. And yet the signals arriving from those worlds are so attenuated, so compressed into the noise floor of even the most advanced telescopes currently operational, that detecting the presence or absence of an atmosphere on some of them has already required dozens of hours of James Webb observation time. Detecting a biosignature ensemble, not one molecule, but a pattern of molecules, co-occurring at abundances that together strain abiotic explanation, would require a sensitivity and an observing commitment that current facilities cannot easily provide. This does not mean the search is pointless. It means the search is harder than the optimistic framing that preceded the Phosphine case typically acknowledged. There is a specific kind of scientific confidence that forms around a methodology before that methodology has been seriously tested. Biosignature science had that confidence in 2019. The frameworks were elegant. The candidate molecules were well chosen. The detection strategies were theoretically sound. What was missing was a real test case, a world complex enough to challenge the framework, close enough to study carefully, chemically ambiguous enough to expose the assumptions embedded in the models. Venus provided exactly that test. It was not a gentle one. The Phosphine case did not simply reveal a calibration error in a data pipeline. It revealed that the gap between detecting a signal and interpreting its cause is not primarily an instrumentation problem. It is a knowledge problem. It depends on how well we understand the chemistry of the world being observed. And that understanding is always partial, always built from incomplete data, always open to revision when new measurements or new laboratory results arrive. For Venus, after 60 years of study and multiple dedicated spacecraft missions, that understanding turned out to be partial enough to prevent a definitive reading of a single molecular detection. For a world 40 light-years away that has never been visited, never been sampled, known, only through the brief dimming of its host light as it passes across our line of sight. The gap is not smaller. It is wider in every direction. There is a version of the future in which this problem is solved, in which the extremely large telescope and its successors achieve the sensitivity required to characterize exoplanet atmospheres in meaningful detail, in which missions to Venus return direct atmospheric samples and close the Phosphine question permanently, in which biosignature frameworks become robust enough that a detection carries genuine evidential weight rather than the kind of ambiguity the Greaves paper ultimately produced. That future is not impossible. The trajectory of observational capability, extended forward several decades, points toward instruments that would have seemed implausible from the vantage point of 2020. But the timeline of that progress sits in uncomfortable tension with a different kind of timeline. The search for life beyond Earth is not merely a scientific program. It is an attempt to answer the question that the Fermi paradox puts most bluntly: whether intelligence, complexity, and the particular kind of chemistry that produces observers capable of asking questions is rare or common in a universe that has had 13 billion years to try. Every year that passes without a confirmed detection is not neutral. It is data. It incrementally adjusts the probability distribution over possible answers in a direction that is difficult to look at directly. Venus was supposed to make the search easier, a nearby world, a familiar molecule, a well-constructed methodology. Instead, it demonstrated that the search is harder than it looked from a distance, that the nearest test case produced ambiguity rather than clarity, and that the interpretive frameworks underlying the entire enterprise are more fragile than their elegance implied. The planet that was supposed to be easy turned out to be a lesson. The lesson was not that life is absent from Venus. It may be there, in the clouds, in forms and concentrations that better instruments and direct sampling will eventually reach. The lesson was about what it means to search for something whose presence you cannot verify and whose absence you cannot prove, using tools that are always operating at the edge of what the question actually requires. The universe does not make this easy. It never promised to.